Have you ever stopped to think about the invisible force that powers pretty much everything around us? It's this amazing secret partnership, a deep connection between electricity and magnetism that was hiding in plain sight for centuries. Okay, let's dive into the incredible story of how we figured it all out.
So here's our game plan. We're going to start with a total accident that connected two forces everyone thought were separate. Then we'll figure out how to actually see these invisible fields and even shape them to our will. After that, we'll master the rules that turn this invisible force into real motion. And to wrap it all up, we'll see how these exact same ideas are working right now to keep you safe in your own home.
All right, let's get right into it. Our story kicks off with a complete accident. This is the moment the world stumbled upon electricity's secret force.
You know, for the longest time, science treated electricity and magnetism like two totally different things. One gave you sparks and shocks, the other made compass needles point north. No connection. But what if they were secretly working together all along?
Well, that question got answered by pure chance back in 1820. A scientist named Hans Christian Ørsted was in the middle of a lecture, and he just happened to notice that when he turned on an electric circuit, the needle on a compass sitting nearby twitched. Just a tiny little movement, but the implication was absolutely massive.
And the experiment itself? It couldn't have been simpler. A wire, a power source, and a compass. That's it. But the result was a revolution. The second that current started to flow, the compass needle moved, proving for the first time that electricity actually creates a magnetic effect. With that one little twitch, the wall between two of nature's fundamental forces just came tumbling down.
So that leads us to section 2. If electricity creates these invisible magnetic fields, how on earth can we see them? How do you map out the invisible architecture of magnetism? So how do you see something that's invisible? Well, you use a clever little trick. If you sprinkle tiny iron filings around a magnet, you can actually see its field. Each and every one of those little filings acts like a teeny tiny compass needle, and they all line up perfectly along these lines of force. And just like that, this invisible power reveals itself in this beautiful, elegant pattern.
And these patterns aren't random at all. They follow very specific rules. Magnetic field lines are always complete closed loops. They flow out of the North Pole and into the South Pole on the outside of the magnet, and then continue from south to north on the inside. They can never, ever cross, because think about it, a compass can't point in two directions at once. And you can easily spot where the field is strongest, right near the poles, where all those lines are bunched up together.
Okay, which brings us to section 3. If we know that current creates a magnetic field, the next obvious question is, can we control it? Can we actually shape it? And the answer is a big, fat yes.
Now, to understand the shape of the field that a current creates, we need our first tool. This is the right-hand thumb rule. It is a super simple, super handy way to figure out which way the magnetic field is spinning around a wire. Go ahead, try it with me right now. Hold up your right hand. Imagine a wire where the current is flowing up towards the ceiling. So point your thumb straight up. Now curl your fingers naturally around that imaginary wire. See how they wrap around in a counterclockwise direction? That's it. That's the direction of the magnetic field. It's simple, it's elegant, and it works every single time.
Now, what happens if we take that straight wire and we wrap it up into a tight coil? Well, we get something called a solenoid, and this is a brilliant way to concentrate that magnetic effect. When you run a current through it, the solenoid behaves almost exactly like a regular old bar magnet.
So here's the crucial difference, and this is the whole point. A bar magnet is permanent. It's always on, you can't turn it off. But a solenoid, which is really just an electromagnet, is controllable. We can switch it on and off just by flipping a switch on the electric current. This incredibly simple idea is the foundation for everything from those giant cranes in junkyards to the electric locks on doors. So we can create and shape magnetic fields. Now for the really fun part in section 4, how we turn that magnetism into actual physical motion.
Here's the key principle. If you take a wire that's already carrying an electric current and you place it inside another magnetic field, say between the north and south poles of a big magnet, the two fields interact and the wire gets pushed. It literally experiences a force. This one concept is the beating heart of every single electric motor on the planet.
Okay, but which way does the wire get pushed? For that, we need our second tool, Fleming's left-hand rule. Now, pay attention here. This is the left hand, not the right. This rule is specifically for figuring out the direction of the motion or the force. Let's do this one together. Hold up your left hand and make an L shape with your thumb and forefinger. Then point your middle finger straight out. Your forefinger points in the direction of the magnetic field. Your middle finger, or center finger, points in the direction of the current. And that leaves your thumb, which gives you the thrust, showing you the direction of the motion or force. So think field, current, motion, FCM.
Now, it's super easy to mix up these two hand rules, so here is the ultimate cheat sheet. It's actually really simple. Use your right hand when you only have a current and you want to find the direction of the magnetic field it's creating. Use your left hand when you have both a current and an external magnetic field and you need to find the direction of the force that results from their interaction.
Okay, for our final section, let's bring all this theory right back home. Literally, how do these invisible forces and all these rules play out in the electrical circuits that are running through your walls right this very second?
Well, in a standard home circuit, you've basically got 3 wires. There's the live wire, usually in red, which brings the high voltage current in. You have the neutral wire, which is black, that completes the circuit and carries the current back out. And then there's that third one, the green wire. That's the earth wire, and its only job is safety.
Here's the thing. During normal, everyday operation, that green earth wire does absolutely nothing. No current flows through it. It just sits there. So what's the point? Why is it so incredibly important, especially for appliances that have a metal body like a toaster or a washing machine?
Imagine this. Inside your toaster, the red live wire frays and accidentally touches the metal casing. Instantly, the entire metal body of the toaster becomes electrically live and incredibly dangerous. But because that metal case is connected to the green earth wire, the electricity now has a super easy, low-resistance escape route. A massive surge of current rushes down that wire straight into the ground. This huge current spike creates a strong magnetic effect inside your circuit breaker, which trips a switch, or it simply melts the thin wire inside an old-school fuse. Either way, the power is cut in a fraction of a second, long before you could ever touch it and get a shock. It's an absolutely brilliant safety system, built on the very principles we've been talking about.
So we've gone all the way from Ørsted's lucky accident to the life-saving circuits running in our homes. We've seen that an electric current creates a magnetic field and that a magnetic field can create a force on that current, which really leaves us with one last huge question. If electricity can create motion, could we flip it around? Could we use motion inside a magnetic field to create electricity?